Good afternoon. So we will wait for 2 more minutes and then we'll get started.
Good evening, ma'am. Okay, all right.
Can you please mute yourself? Thank you. So we'll get started. So this is the week 4 live session of the course Environmental Quality Monitoring and Assessment. And I am Niketa. I am a PhD student at IIT Madras. And so before we start today's class, I want to ask you if you have any questions or doubts from this week's lectures.
Not right now, ma'am. Could you
Not
please
right now.
suggest any? Yes, could you please suggest any writer's name so that I can download the PDF of that book and I can study properly
I think
and
reference
better?
books and details will be given in the course details, no, on the NPTEL website.
Okay,
Have you
that
checked
book
it?
only. Okay,
Yeah,
okay. Thank you, ma'am.
yeah, thank you. So, you said you didn't have doubts right now. So, have you been through all the lecture videos?
Yes.
Okay. So, in case you have any doubts, you can maybe post it on the forum, or you can just ask in the next class.
Okay, thank you, ma'am.
Okay. So, this week's lectures were about sample analysis and extraction mostly. So, we'll start with sample analysis. So, what is a sample? Why do we need a sample?
The sample is mixed into the water, right? So to examine the water, we need the sample.
Yeah, like if we have a contaminant or a pollutant, which is a chemical that needs to be analyzed, then like
Yes.
we if we want to detect or find out if the river is actually polluted or not, in that case, we will take a small portion of the river water or lake water or any other environmental media. We will take a small portion of that, and then we will do analysis with that. So that small portion, which is called as a sample, and the sample should always be representative. So do you know what this means? What is a representative
What?
sample?
No, please elaborate, ma'am.
Sorry.
Please explain.
Okay. So, a representative sample is one which correctly represents the conditions in the environmental media. Like, if you take a river water sample, then and if it is contaminated, then if you just take it at a point where there is very low contamination, it's going to show you biased results. And if you take it at the mouth of the point, if you take it at the point where there is effluent or there is discharge of any wastewater, then that place is going to show a very high concentration of the contaminant. So that's why we need to take multiple samples and we will do an averaging. So we need to ensure
So
that
contamination is the main point.
contamination is the main point. I didn't get you.
You told just right now. Contaminated
No,
water.
what I meant was it's important that we take a representative sample because otherwise we will get biased results. Like in some, if we take a sample which in which if we take a sample at a point where there is no contamination, but further downstream there is going to be some contamination, then that's a problem, right? Because we don't exactly get the correct conditions. And similarly, if we take a sample at the point where there is effluent coming in, then that is also wrong. So
Hmm.
it's important that we need to have averages of various samples so that it's representative of the actual conditions in the river. So that's why it's
Mhm.
important to take a representative sample, and that can be done in many ways. Like we can take it, we can do sampling over a period of time, and then we can average it. So yeah, that is important. Okay, so I've just realized that my screen is not visible. Okay, so yeah, that's representative sample.
Your screen is not visible, ma'am. Right now it is.
It's visible now.
Yes,
Yes.
yes, yes, ma'am.
Okay. All right. So then, after taking the sample, what is the next step?
Put it into the proper instrument for analyzing.
Yeah, the next step is analysis, where we will check the concentration of the chemical that we will check the concentration of the desired chemical. So that can be done by using various kinds of instruments. So in the previous class, we have seen that we have chromatography instruments. Can you give me examples of chromatography instruments which we discussed in the previous class?
Gas chromatography,
Yeah, or GC in short.
HPLC.
Yeah,
I
that is liquid chromatography.
Mm.
So these are the two main types of chromatography instruments. Other than this, we also have ion chromatography or IC. So all these are used for finding out the concentrations of various substances or compounds or even ions. So after this, so we need to before analysis, there is one major step. So you just told me what are the different types of instruments. So now it is important to identify which instrument has to be used. So what is the factor which decides which, how will we decide which instrument needs to be used?
The constituents present in water.
Constituents, yeah, there could be more than one constituents, but
We can
how
use
will,
pH meter to measure the pH, a
right?
thermometer to measure the temperature, conductivity meter to measure the
Yeah,
conductance.
yeah, you're right. But you have all of these different parameters that need to be measured, right?
Ah, yes, yes.
So if you have just one particular parameter, then how will you decide? So if you have just one parameter, like for example, I want to measure what is the concentration of this organic compound, then I may go for a liquid chromatography instrument, right? So ultimately, it depends on what needs to be analyzed. Or in other words, what is the compound of interest or chemical of interest
The
that
pollutant.
needs to be, yeah, the pollutant of interest that needs to be analyzed. Because the same sample can have different types of pollutants, and for each of them, you may need different instruments. So, different techniques, not just instruments, we need different techniques also. So, for organics, we can use chromatography, and if you have solids, dissolved solids or suspended solids, then you may need a oven or a furnace, and you may need a filter paper to remove the suspended solids first, and then you will determine how much is the concentration of those solids. So depending on what pollutant you want to analyze, different techniques and different instruments need to be used. So choosing the right instrument is the first step when it comes to sample analysis. But after this, you have chosen the instrument, you have decided what needs to be analyzed. What is the next step?
We can find out the concentration of pollutant present in water from that reading, from the instrument reading.
Yeah, so can we just insert the sample as such into the instrument? So before we, does anybody have anything to say? So before we go on to find the concentration, we need to think like if this instrument will be capable of handling this sample. So we cannot just blindly inject a water sample or a river sample, I mean, a water sample or any other sample without thinking of if the instrument is capable enough to analyze it. So, and also sometimes the instrument may not be able to analyze a sample in its given form. So we need to change its form, convert it into a different form, and then only it can be injected. Are you understanding?
Yes, 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 yes.
Yes.
So, for example, if there is an oil spill and we have a lot of organic chemicals which are present in the oil, may not be oil spill, could be just another chemical contamination in soil, and we want to find out the concentration of this chemical present in that soil. So soil is solid, right? So imagine you have a soil sample like this which is covered with a layer of chemical. So you can't just inject the solid samples into maybe a liquid chromatography instrument, right? So what needs to be done?
It has to be dissolved in suitable solvent.
Exactly.
Solvent is added so that that organic chemical passes into solution.
Yeah. So, in order to make it suitable so that it can be injected into the instrument, what needs to be done is first we have to separate the chemical from the soil, and that can be done with the help of solvents. So, solvents are just chemicals which are used for separating the chemical of the pollutant of interest from the given sample. And once this is done, maybe we can once the separation has been done and now the analyte or the pollutant of interest is in the solvent, then the solvent can be along with the pollutant can be injected into the instrument. So in that case the instrument will be able to analyze the sample. Okay, so what we talked about here, which is mixing the soil along with the pollutant in a chemical which is a solvent. So, this process can be described as extraction. So, can someone define this? What is an extraction process? I just gave you an example of this. So, can you explain it properly?
Suitable solvent is added so that that organic compound goes into solution.
Yeah, so basically, it is a technique to make the analyte easier to
Extract.
analyze. Yeah, so that can be done in different phases. And one of the main reasons why we do this is to make the instrument receive the sample easily. So, like we said, a solid substance having the chemical cannot be injected into a liquid chromatography instrument. We need to make it into a form, convert it into a form which is accepted by the instrument more easily. So, that is one of the main reasons. Can someone tell me the second reason why we do this?
To increase the concentration of the pollutant in that solvent, because the pollutant present in water may be very small, which is below the detection limit.
Okay.
So we can add some solvent so that the pollutant goes into that solvent, small amount of solvent. Then we can easily detect how much of that pollutant is present in that solvent.
Yeah, so is it always done to increase the concentration?
Yeah, increase the concentration.
So, what about the opposite? Can we also reduce?
Now, if solvent added is more, then the solvent can be reduced in volume.
Yeah, so in case your instrument is calibrated in such a way that
Mm.
after extraction, or maybe the concentration of the chemical in the sample is going to be very much higher than the calibration curve or the maximum detection limit of the instrument, then in that case, what would you do? You will try
Dilution.
to reduce
We
the
can increase.
concentration, right? And how will you do that? By adding more solvent.
Mm-hmm.
So
Yes, yes.
extraction can be used to change the concentration of the chemical, and to bring it to an optimum range. So by change, I mean we can increase or decrease the concentration. That depends on what will be the range of concentrations which can be detected by the instrument. So, in order to use a chemical as a solvent, what is the major criteria?
The pollutant should be more soluble in that solvent.
Yeah. So, in other words, we can say that we must ensure that the chemical which needs to be analyzed has more affinity to the solvent rather than the water or soil or anything. So, what do we mean by affinity here?
Solubility. Highly soluble in the
Solubility.
solvent than in water.
In other words, what is another term for solubility? Not another word, but like by affinity, we mean to have a higher partition constant or partition coefficient. So, if a chemical has a higher partition coefficient towards the solvent rather than the sample, then the solvent can be used and it can successfully uh, remove or separate the analyte from the sample, and then it can be loaded into the instrument. And at the same time, this is the first criteria. So, what is the second one?
Should easily vaporizable.
Okay, vaporizable from. So, vaporization is a form of separation, right? So, why will we separate the solvent?
To increase the concentration. To reduce the volume.
No, I mean, like, yeah, that is the second stage, but I'm asking, like, when you have a sample of water and you have an organic chemical which is soluble, dissolved completely into that sample. Now you want to extract the chemical out of that liquid sample, then you are adding a solvent. So um, now if the solvent is also mixing along with the sample water, so how will you separate both? So in order to avoid this, our solvent must be immiscible with the sample. And in case our sample is a liquid or maybe water, then it should be immiscible in water. What do we mean by immiscible here? Should not mix. Is this clear?
Yes, yes, yes.
Okay. So now coming to the different types of extractions. So can you tell me what are the different types?
Liquid extraction,
Yeah.
solid phase extraction.
So what's the difference between both?
In solid phase, we have to use suitable adsorbent. Solid.
Okay. And then? Then how will you
Then the
separate?
adsorbed substance should be dissolved
Using what?
using a solvent.
Yeah. So in a liquid extraction method, we will have a liquid and the chemical will be completely dissolved in that liquid. Now we will have another liquid which is the solvent. So the solvent will be added to this sample, and because of the higher affinity of the chemical of interest towards the solvent, so this chemical will get dissolved into the solvent more than its solubility in water. So when that happens, all of this will be transferred to the solvent, and since both the solvent and sample are in liquid phase, and we are directly extracting the chemical from using a liquid from another liquid, so then it is called as liquid extraction. But when it comes to solid phase extraction, what happens is that you have a chemical and it is present in a liquid, and it cannot be extracted by adding a liquid solvent. So in that case, what we do is we add some kind of an adsorbent, or we pass this sample through an adsorbent. So this adsorbent will absorb all the chemical, and later this will be washed, or this will be flushed with the solvent, and from this we will get the chemical along with the solvent. So since this involves the additional adsorbent which is a solid substance, so this is called as solid phase extraction. And when it comes to extraction, we need to make sure that the efficiency of the extraction process is high. If it's not high, if it is low, then what will happen? So if your extraction efficiency is going to be low, then what will happen?
Concentration of the chemical in the solvent will be less, that is below the detectable limit.
Not
in the instrument.
necessarily, may not always happen that way. But there is another thing. So, in case the efficiency is low, for example, you have 100% of the chemical in the sample and only about 85% is getting adsorbed, then it is a loss, right? So you have only 85%, remaining 15% is going to be in the sample itself. So when you analyze this, this will tell you, I mean, when you analyze the chemical that is coming out of it, it is going to be only 85%. It's not 100%. So there is a loss. So if we have a lower efficiency, it means there's a loss of the analyte somewhere in the process, either during solid during adsorption, or maybe after adding the solvent. The solvent may not have 100%. I mean, the solvent affinity might be slightly less, so the concentration in the solvent may be not 100%. It could be lesser than even 85%. Maybe it's around 80%. So your final concentration will be around only 80%. So in order to avoid all this, we must ensure that the process has a high efficiency. Yeah, so elaborating on this, there are various ways in which there could be loss of analyte. So, can you tell me what are those? So, even if your efficiency is low, we must have the, I mean, we must be knowing correctly how much is that efficiency going to be. So, if you think that you are going to get 100% efficiency, but actually it is only 95%, then that's a problem. So, even if it is less, we must know what is the efficiency.
During extraction of the chemical in a solvent,
Yeah. So, what are the possible ways in which there could be losses during extraction?
the solvent may slightly vaporizes or volatilizes.
Yeah, so evaporation can happen.
Evaporation.
Any other losses? Any other way of loss? So simply by while transferring from one container to another container, there could be some spillage. Like the chemical may fall somewhere while transferring. So that is a one type of loss. And sometimes there could be error in measurements. So there could be error in the measurement of mass or volume. So if you incorrectly measure the volume, then your concentration is going to change. Same goes for mass. So these are the ways in which there could be any loss. Like you can maybe the volume is estimated slightly higher than the actual. So in that case, there could be reduction in the concentration. Okay. So, during analysis, so when we use standards, there are two types of standards. One is internal standard and the other one is external standard. So, can you tell me what is an internal standard? What is an internal standard? So, generally, what is a standard?
It's a chemical of known composition, known quantity.
Composition and maybe
Strength is
uh,
known, concentration is
sometimes
known.
even the concentration is known.
Mm.
So, and it is known to be true. So, such substances are called standards, and we use this during calibration. So, when we say internal standard, what does that mean? What is an internal standard?
It's a chemical added to the liquid or the water.
No, but that can be anything, right? Why do we specifically say it is internal standard? So, in some cases, what happens is when we have a sample and we have the pollutant of interest in this sample, but there are other pollutants also. Now, we don't know how these pollutants will behave. Sometimes these other pollutants will interfere with the analysis of our desired pollutant. So, in order to check this, in order to check if there is going to be any reduction in the concentration of the chemical due to other pollutants, we use internal standards. So, internal standards are nothing but they are chemicals which so they are chemicals which mimic the pollutant. So they are very similar in their behavior. So just like the pollutant, I mean, they behave just like the pollutant. So when you need to check if the pollutant's concentration is going to be affected by other pollutants or contaminants in water, we use internal standards to check, because internal standard is something which we whose concentration we already know. So when we add something of known concentration and we are checking if there is any change in concentration later on, we can assume that the same change is going to happen with the chemical of interest also. Are you following?
Yes, yes, yes. Yes.
Yes.
So that is why we use internal standards, because it is going to mimic the behavior of the pollutant. And if there is going to be any interference due to other pollutants, then it is going to show us that the analyte's concentration will change because of the presence of these pollutants. and it also tells us by how much. So accordingly, we can add or subtract the concentration of the chemical that we want to measure. And this is especially useful when you want to analyze a sample where where it is not, the analyte is not added externally. So this is the case when we want to analyze maybe a water sample which already has some known which has some unknown concentration of the chemical, and we want to check how much it is, but we don't know how it will behave in the presence of other contaminants, and how much it is going to like how much efficiency it is going to show for extraction. So all this can be done with the help of an internal standard. So internal standard is going to behave just like this chemical. So using the internal standard itself, we can say how much efficiency of extraction is going to be there. So another type of loss is the loss due to adsorption. So sometimes, where does this happen? Loss due to adsorption?
By the container.
Yeah. So in case our sample is our analyte is organic, it is an organic chemical, and we are also using an organic container, say like plastic or something. So there is going to be a attraction between the chemical and the wall of the container, and it could get adsorbed there. So that is going to reduce our concentration of the chemical in the sample. So, like I said previously, so efficiency is also known as recovery or recovery percentage, which is equal to the amount of analyte recovered divided by the initial concentration of the analyte. So when we say the recovery percentage is 80%, what we mean is we will check what is the amount of analyte which is recovered after the extraction process. So if it is around, let's say the initial concentration is 1 milligram per liter, and we are recovering only 0.8 milligram per liter. So the recovery percentage is going to be 0.8 by 1 into 100, which is 80%. So when we say it is 80% recovery or 80% efficiency, it means uh, maybe like only 80% of the solvent is getting properly extracted. So the rest is like it's lost. So now that we have seen the different types of errors, so now we will see what are the different ways to avoid these errors. So can you list out what are the various ways? Can you tell me what are the different ways in which we can avoid the errors?
Error means loss, isn't it, ma'am?
Yeah.
There should not be any space between the liquid level and the top of the container. That head space, there should not be any head space.
So headspace, yeah, but that is like only for one specific instrument, right? So when you use a GC or something, that is when you have this issue. But generally, when we use extraction, so there are different ways in which we can avoid the errors, not just extraction. Um, so when we have analysis or when we do instrumental analysis also, there are some errors and like what we discussed, and there are different ways in which we can avoid those errors. So first one is using correct standards. So if you use proper lab standards, so these are also called external standards. So basically, we use standards to avoid errors, but when we use external standards, we get some errors when compared to internal standards. So why that happens is because in internal standards, we know we can get information about how the chemical or analyte is going to behave, and accordingly, if there is any loss, we can predict that loss also. But when we use external standards, we will not be able to do that. So an external standard is it's a standard, but unlike an internal standard, it won't be added to the sample. So if you want to analyze a substance from a given sample, you will take the same substance and you will prepare a known concentration of that, and you will use for the calibration. But in case of an internal standard, you are putting this chemical into the sample itself along with the analyte of interest. So while running the instrument, if there is any loss in the internal standards concentration, we are able to predict how much loss will be there in the analyte. But when we use an external standard, we cannot do that. So that is the difference between the two. Another option is we can use surrogate standards. So surrogate standards are very similar to internal standards. They are going to behave just like it, just like the compound of interest, but they are not that. They are something else. And the third method is by using matrix spiking. So, what is matrix spiking? Can someone explain? First of all, what is matrix?
chemical which is present or any substance which is present in excess in large quantity.
Are you sure?
Think so.
Okay, a matrix is any media. So if we have a water sample, then water is the matrix in which the analyte is present. Similarly, when we say a soil matrix, we mean that the soil is the sample in which the chemical is present. So matrix is basically the medium in which the chemical is present. So spiking is basically increasing the concentration or increasing the mass of a substance. So what we do in matrix spiking is we will divide the sample into two portions. And we will be adding the standard to 1. That means that in one of the sample is already having the analyte. So in one portion of the sample, we will be having the analyte plus we will be having the standard. And in the second portion, we will be having only the analyte. So when we analyze these two samples, so the difference in concentrations of both will tell us how much loss is happening. Is this clear?
No, no, ma'am.
Okay, what we mean here is we are dividing the sample into two portions, and in one of them we are adding a known standards which is having a known concentration, and in the other one it doesn't have any standard at all. So when we analyze it, so the difference in concentration of both these samples, sample 1 and 2, will tell us how much of the added standard is lost.
Okay, okay.
Because we know this concentration. So in the second sample, there is no analyte. There is no standard. So this, since we already know what is the standard concentration, and it is going to be slightly higher than the analyte concentration, so we will know that okay, so this is the loss, and similar behavior can be expected from the analyte also. Is it clear now?
Clear, clear, ma'am.
Okay. Others?
Okay, ma'am.
Clear? Okay, so then when we do instrumental analysis, sometimes there will be cases of false positive and false negative. So, what's the meaning of these two terms?
False positive means more than the expected, more than the actual concentration,
Yeah, and false negative?
and less than the actual concentration.
Yeah. So, why do we get these two results?
Due to loss during the steps involved in the process.
What will come with loss, negative or positive?
Uh, ineffective.
Yeah, sometimes if
Sometimes
you
sunlight may also evaporate along with the solvent. In that case, we'll get
yeah, sometimes maybe the analyte will get absorbed into some part of the instrument, so then it will become a negative. Or sometimes what happens is there could be some accumulation from previous analysis. Maybe the same chemical was analyzed previously, and at that time there was some accumulation in the instrument. So now, when we are injecting the same sample again, the accumulated chemical will tend to come out, and it will show a higher concentration of that chemical. So this could give rise to false positive. So false positive and false negatives are these two are errors, and in order to avoid this, we need to run blanks. So what are blanks?
without the analyte.
Yeah, just the maybe waters or just any solvent without the analyte. So if we can run that blank, and if still there is any chemical that is present in that which is accumulated inside the instrument, and if we run blank, and if the blank shows signal, which indicates the presence of that chemical, it means that there is some accumulation in that instrument. And how much is getting accumulated, that also can be determined. So when we run blank, after we run the blank, we must subtract it from the our analysis result. So if there is any signal, so that signal which corresponds to that chemical needs to be subtracted. Okay, so do you have any questions from this class, or shall we move on to the assignment problems?
We'll move on to the assignment.
Okay. Others, do you have any questions?
Not right now.
Okay. So, have you tried solving the problems in assignment 4?
Only for few.
Okay. So, first question is, which of the following is a valid reason to extract an organic chemical in water to another solvent for the purpose of chemical analysis using an appropriate instrument Options are some analytical instruments cannot accept the water samples directly. Second one, concentration of chemical in the water sample is below the detection limit or the calibration limit of the instrument, and the extraction will facilitate the concentration of the analyte. Third option, all environmental samples must be extracted. Fourth option, all standards mention that all water samples must be extracted. So, which is the correct answer?
1 and 2.
Okay. So, some analytical instruments cannot accept the water samples directly, like what we discussed. And the second one is the concentration is below the detection limit or not within the optimum range. So, in that case, also we do extraction, like we previously discussed. So, the third and the fourth point, it's not actually valid. So, it's not a valid reason for doing the extraction process. So, that's why we the correct options are A and B. Okay, so the second question in the selection. Of the solvent for extraction of organic chemicals using liquid extraction. from water. So the question is, in the selection of the solvent for extraction of organic chemicals using liquid-liquid extraction from water, which of the following parameters of the solvent are most directly relevant for the purposes of extraction? So options are: number one, viscosity; number two is density; three is partition constant; four is volatility; five is solubility. So what is viscosity here?
Resistance to flow.
Yeah. So when we have a liquid, it will have different layers. So these layers will be sliding on each other. And when we say a liquid is highly viscous, then it means that the layers have a higher resistance between them, which will prevent the sliding of the layers, and this will affect the movement of those of the liquid in general. So is this a relevant parameter?
No.
Yeah. So this is not going to affect our extraction efficiency in any way. And what is the formula for density?
Mass per volume.
So is the density of a solvent important?
No, no, no.
So what about partition constant? We just discussed about this. Is it an important parameter?
Yes, yes.
So it is important that the chemical will should have a higher affinity towards the solvent. So that's why the partition constant of the chemical is an important parameter. So, and the next is volatility. So when we try to, after extraction, when we try to separate the liquid from the, sorry, separate the solvent from the sample, then, separate the analyte from the solvent, it is important that the solvent should be volatile so that we can easily separate the solvent from the analyte. And then comes solubility. So it is important that the chemical should be highly soluble. So that is why in the solvent. So this is also correct. So the last three options are correct. Okay, so the third one. Which of the following methods are commonly used to extract organic analytes from water? The first option is Soxhlet extraction. The second option is solid phase extraction. And the third option is liquid extraction. And the fourth option is ultrasonic extraction. So, which is the correct answer?
Solid phase extraction, liquid extraction.
Why?
In
What
the
about
liquid
Soxhlet?
solid phase, we can use suitable absorbent. And liquid phase, liquid extraction, we can use suitable solvent.
Okay, what about Soxhlet extraction?
Soxhlet only for solid materials. So if you want to extract the solid,
Yeah. So,
uh,
Soxhlet extraction and ultrasonic extraction are both used for solids. So, since they are asking from water, so the correct options are 2 and 3, or B and C. So, the next question is, which of the following apparatus or methods can be used So, which of the following apparatus or methods can be used in the concentration of an organic analyte in a solvent after extraction? First one is boiling. Second one is Keter dilution apparatus. Third one is rotary evaporator. Fourth one is nitrogen blowdown. Fifth one is microwave oven. So, can we use boiling?
yes,
So, if you have a volatile sample, will you prefer to boil it
we can use boiling.
for a volatile sample?
Volatile. Not
What
for
will
volatile.
happen? What will happen if we boil it?
Yeah. That's not suitable.
What will happen? Why it is
It
not suitable?
also vaporizes. The analyte also vaporizes along with the
Oh,
liquid.
see, boiling will result in a very highly vigorous reaction. So sometimes maybe the glass tube or whatever may burst. because a lot of vapor may be generated, so it is not advisable. So generally for volatile solids, volatile substances, we won't prefer boiling. We will rather go for evaporation because that is a very easier technique compared to boiling. It is not safe also. And also along with that, like you said, there could be loss of analyte. So what is the Kudana Danish apparatus? Can you tell me what's the difference between Kudana Danish apparatus and a rotary evaporator? Okay. So this apparatus will use hot water in circulation to evaporate the solvent. Whereas in a rotary evaporator, we will have a hot water bath. So this is the difference in the design. So based on the design, it is further. There are many other differences also. So the basic difference is like this. Like this will use a hot water bath for evaporation, whereas in a KD apparatus, we will circulate the water through a column and it will evaporate the solvent. And in a rotary evaporator, we also use a condenser. So whatever solvent is getting evaporated, it will get condensed and that can be collected separately. So what is nitrogen blowdown?
By passing nitrogen gas
What will happen if we do that?
for the removal of air, I think, for the removal of dissolved air.
Dissolved air is where?
Um,
Dissolved air should be removed from where?
mm,
We don't have any dissolved air to remove, so nitrogen
no idea.
blowdown is mainly used for removing the solvent. So when you pass a stream of nitrogen gas, it will slowly evaporate the solvent. So that is why it is mainly used. And then a microwave oven. So this is used for extracting the analyte from the solids, but it is not exactly used for concentration. So the correct options are 2, 3, and 4. Next question. So this is a numerical question. So 1 liter of water sample was extracted with 30 ml of solvent, and then that 30 ml was separated and concentrated to 1 ml, and 1 microliter of this 30 ml was injected into a GCMS, and the concentration was determined. So that concentration is 1 microgram per liter. So what is the initial concentration in 1 liter of the water sample? So for this, we need to understand the process first. So here they are describing how they have done the extraction. So they've taken 1 liter of water sample, and in that 1 liter of sample, they have added 30 ml of solvent. So and after that, they have concentrated this. They have separated this solvent, and then they have further concentrated it to 1 ml. So this 30 ml is reduced to 1 ml, and then this from this 1 ml they have taken 1 microliter for analysis, and from that they are getting 1 microgram per liter concentration. So 1 microgram per liter is the final concentration in 1 microliter of the substance. So 1 microgram per liter was obtained from 1 microliter of the solvent. And if we determine how much of mass is there in this 1 microliter, so in 1 microliter, how much mass of the analyte will be there? So for that, we have to take this concentration, 1 microgram per liter. And since they have given in the units of microgram per liter, we will be converting it to microgram per microliter. So how many microliters is 1 liter?
Ten power six.
So instead of writing 1 microgram per liter, I can write 1 microgram by 10 power 6 microliters. Right? So this means in 1 microliter, there is going to be 10 power minus 6 micrograms. So since this was obtained from 1 ml, so how much mass will be there in 1 ml? In 1 microliter, there is 10 power minus 6 microgram. So in 1 ml, how much will be there? So to find that out, 1 microliter will be equal to 10 power how much? How much 1 microliter equals to how much ml?
10 power 6.
No,
10 power 3.
milliliters.
10 power 2.
10
ml
power
is 6.
6 is for liters, right? So 1 microliter is going to be equal to 10 power minus 3 milliliters. And if I say that in 1 microliters, I am having 10 power minus 6 microgram. So, so 1 microliter is 10 power minus 3 milliliters, or 1 milliliter is going to be 1000 microliters. Correct? So if in 1 microliter there are 10 power minus 6 microgram, so 1 ml will have 1000 into 10 power minus 6 micrograms, which is, how much is this? How much is this? 1000 into 10 power minus 6.
10 power minus 3.
Yeah. So 10 power minus 3 microgram of that chemical is there in 1 ml. So here this 1 ml is all of that chemical. Okay. So assuming there is no loss anywhere and there is 100% efficiency in transferring the chemical from the sample to solvent, and it is further concentrated into 1 ml. So this 1 ml is 100% of whatever sample was there initially. There is no other loss, and this 1 ml has the entire mass of that chemical. Is this clear? No response?
No, ma.
Okay.
I didn't repeat the whole thing once. One more.
Yeah. So what I was saying is, in 1 liter they are having some chemical. Okay. So that they are extracting by adding a solvent, and that solvent they are reducing to 1 ml. So what is happening here is whatever chemical was present in this 1 liter, it got absorbed or it got dissolved into the solvent, and all of it has been taken to another container. So initially the solvent volume was 30 ml. 30 ml of solvent was added in which all the chemical got dissolved. So the 30 ml was further reduced to 1 ml. What happens here is while reduction, only the solvent is getting evaporated, the analyte will stay the same. Agreed?
Yes, 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 yes.
Yeah.
Okay.
So only the solvent is getting evaporated. The analyte will be as it is, and it will be present in 1 ml of the solvent. Correct?
Yes, ma'am. Yes, yes, yes.
So all the analyte mass is concentrated in 1 ml volume here. So now we are determining how much mass is there in 1 ml. So that we have determined by using the concentration that we have got from GCMS. So we have just done some kind of back calculation to find out how much mass of the analyte is there in 1 ml volume. So this is the final answer that we got. It is 10 power minus 3 micrograms. So there are 10 power minus 3 microgram of that mass in 1 ml of this sample. So since this is the entire mass of the chemical which is present in 1 ml, so this 10 power minus 3 microgram was what was present initially in 1 liter. Is it clear?
Yes.
Others?
Okay. Yes, ma'am.
Okay. So initially this 10 power minus 3 microgram was only present in 1 liter, which was further concentrated to 1 ml by adding 30 ml of solvent and then evaporating that solvent. So, and then from 1 ml of that substance, we have taken 1 microliter for analysis, from where we have got the concentration as 1 microgram per liter. So, in 1 microliter, there is 10 power minus 6 microgram of mass of the chemical. So, in 1 ml, how much will be is what we have calculated. So, that is 10 power minus 3. So, this is what is there in 1 ml. So, this is the entire mass of the chemical which was present initially in 1 liter. So now they are asking how much is the concentration of the chemical in 1 liter. For that, what we have to do, concentration is, what is the formula? Mass of the chemical divided by the volume of water. So we know that the mass of chemical is 10 power minus 3 microgram and volume of water is 1 liter. So this is going to be 10 power minus 3 microgram per liter. So they have asked in terms of nanograms. So can you convert microgram to nanogram? How will we convert?
1 microgram is equal to 10 power minus 3 nanogram. It is.
Okay. So what is this in nanograms?
Mm. 10 power minus 6.
How?
1 microgram is equal to 10 power minus 3 nanogram.
Okay. No, no, no. 1 microgram is 10 power 3 nanograms. 1 microgram is
Yeah.
1000
Yes,
nanograms.
yes.
So if we have 10 power minus 3 microgram, it is equal to 1 nanogram per liter. So this is the answer in this unit. Next question. So in problem 5, it was not possible to separate the entire 30 ml of the solvent added. Instead, only 20 ml could be recovered. If this was concentrated to 1 ml, 1 microliter of this final concentrated extract was injected into GCMS and the concentration of 1 microgram per liter was obtained. What is the concentration of water in nanograms per liter? Okay, it is the same question, but what they are saying is that initially 1 liter of water was there and they have added some amount of solvent to extract the chemical into the solvent. And from this, instead of 30 ml, they are only able to get 20 ml. Remaining 10 ml along with the analyte or chemical is present in the sample itself. It was not possible to take it out. Only 20 ml was taken and that was further concentrated to 1 ml by evaporation. And from this 1 ml, 1 microliter was taken and it was analyzed using a GCMS. And the concentration was obtained as 1 microgram per liter. Understood?
Yes.
Okay. So now we already know that in this 1 ml 1 ml volume, there is 1 nanogram of mass of chemical present. Now, this is in 20 ml and not in, this is from 20 ml extraction and not 30 ml extraction. Okay. So what we have got here is from 20 ml. So if we take the entire 30 ml, imagine this, like if all the 30 ml of the solvent was able to be separated from the sample, then the mass of the chemical will be higher or lower?
Will be higher.
Higher, right? Because 10 ml is already left behind. So if this 10 ml was also there, then the mass of the mass of the chemical will be higher. So we'll just do a simple cross multiplication. So let's say there is x nanograms of chemical in 30 ml and 1 nanogram in 20 ml. So x will be equal to 30 by 20 and this is
1.5.
yeah. So mass of the chemical in 30 ml of the solvent is 1.5 nanograms. So what will be the concentration in 1 liter? So 1.5 nanogram is the mass of the chemical in 1 liter. What is the concentration?
Same thing,
Mass
1.5
into
nanogram.
volume.
Yeah, how much is that? How much is this?
1.5 by 1
What are the units?
nanogram per liter.
Yeah, so it is 1.5 nanograms per liter. The next question is, which of the following is used for estimating the recovery of an organic analyte during extraction? Options are external standard, internal standard, surrogate standard, and gold standard. So, which is the correct answer?
One, two, and three.
No, actually, internal standard is it will behave just like the chemical, but it's not exactly used for the purpose of extraction. So, for extraction, we go for surrogate standard. So, internal standard means it's the same substance. So, but surrogate means it behaves like that substance. Understood?
Yes, ma'am.
Okay, the next question. Which of the following is a desired characteristic of a surrogate standard? Options are the surrogate must have exactly the same molecular weight as the analyte. Second, so the surrogate standard must not be present. In the sample. surrogate standard can be a radio label. It can be radiolabeled compound that has the same properties as the analytes of interest. And fourth option, calibration of surrogate standard is necessary to obtain the recovery of the analyte. So, answers.
Number 2.
Okay, so if the surrogate is already present, then the results will not come properly. So it should be a substance which is different from the analyte, yet it behaves similar to the analyte. So this is the correct one option. And also looking at other options, so same molecular weight as the analyte, is it necessary?
No need.
Yeah, it's not required. It need not have the same molecular weight. If it is the same molecular weight, then it will be indistinguishable. So that is again a problem. And surrogates are usually radiolabeled compounds which behave the same way as the analytes. So third option is also right. And calibration of the surrogate standard is also necessary because we need to find the loss or difference in the concentration of the surrogate standard. So in that case, we need to have a calibration curve for the surrogate standard also. So fourth option is also correct. Okay, so the next question. So this question is with reference to the tutorial discussed in the lectures. If the bulk density of the sediment is 1400 kilograms per meter cube and volume of sediment is 10 meter cube, then what is the mass of dry solids in kilograms? So they have given the bulk density and they have given the volume. So can you tell me what is bulk density? How do we find the bulk density formula? So bulk density is mass of dry solids by the total volume, which includes the volume of water also. So if they have given bulk density, so and they have given the total volume, which is 10. So with this we can find out what is the mass of dry solids, which is equal to 1400 multiplied by 10. What is this number?
14,000.
Units?
Kilogram per meter cube. Kilogram.
Yeah. So the answer is 14,000 kilograms. Okay, this is a follow-up question. So if the bulk density is 1400 kilogram per meter cube and the volume is 10 meter cube, what is the moisture content of the sediment in mass of moisture by mass of wet sediment? And they are also asking, and they've also given what is the particle density. So the particle density of the solids, which is rho s, it is equal to 2200 kilograms per meter cube, and the density of water is 1000. So in order to find the moisture content, what do we need? What is the formula of moisture content which is given in the question? Mass of water by mass of wet sediment. So in order to find the moisture content, first we need mass of water. So we know what is the total volume. It is 10 meter cube. This includes the volume of solids and the volume of water. So, but they have also given us the particle density of the soil solids. So this particle density is rho s, which is equal to mass of dry solids or mass of dry soil divided by the volume of solids only. So that's the difference between particle density and bulk density. Here we are considering volume of the solid plus the volume of water. Here it is only the volume of solids. Okay, so this is 2200, and this is mass of dry soil, which is denoted by MD, and this is the volume of solids, which is VS. So mass of dry solids is already we found in the previous question, which is about 14,000 kgs. So using this, the volume of solids will be how much?
14,000 by 2,200.
Yeah, how much is that?
14,000. 6.66.
Hmm?
6.3 something.
Okay, so it is
0.636.
0. No, I think you have miscalculated. So it is 6.36 meter
6.3
cube.
something.
So the total volume is 10.
6.36. Yes.
Yeah. So total volume is 10. So this 10 is the sum of volume of solids and volume of water. So we already know volume of solids is 6.36. So volume of water will be 10 minus this. How much is this?
4.36.
3.7.
Sorry,
3.7.
it is 3.64 meter cube. So now we know what is the volume of solids, we know what is the volume of water. So we have the volume of water, so and we have the density of water. So density is the mass of water by volume of water. So in order to find the mass of water, we need we've been given the density and we already have the volume of water. So what is the mass of water?
1 kilogram.
Are you sure? So this is 1000 kg per meter cube, and this is 3.64 meter cube. So now we have to find out mass of water. What is this? We have to find this. We already
364.
have. Yeah, 364.
Hmm.
Check again. So
Sorry,
it is
sorry. 3,
3640 kilograms.
3640.
So now to find the moisture content, we have the mass of water. We also know what is the mass of wet sediment. So we just have to, so mass of wet sediment will be mass of solids and mass of water. So we already know that the mass of solids from the previous question is 14,000 kg. So we are writing that here. And mass of water we just calculated, it is 3640. So together it will be what?
Course. Yes.
17,640.
Yes. So this is the mass of the wet sediment. So the moisture content is equal to mass of water, which is 3640 divided by 17,640. How much is this? Yeah. So it is 0.2. So the moisture content is 0.2. Okay, we've come to the end of this class. If you have any questions, please ask them.
Yes, ma'am. That I asked you in the beginning.
What did you
Any
ask?
other reference? Any other reference book that I can follow apart from that is mentioned?
So what I can do is I can ask the professor and I can let you know.
Okay.
Okay,
Actually,
so
if I get that, I could download the PDF and follow. That's
okay.
why I am asking.
Okay, sure. I'll ask Professor Ravi Krishna and I'll send you a reply. Or maybe in the next class I'll tell you after asking him.
Okay. Thank you,
Oh,
ma'am.
okay, thank you. So, in case there are no other
Okay.
questions, we will be ending this session. Thank you all for joining.
Thank you, ma'am.